Okay, here what we're going to try to do is an acceleration velocity position problem, a very standard looking one. The way we actually want to get them done. This is more about introducing us to the procedure. This is actually a very straightforward one. Probably a little too straightforward, but here we go. Let's looking at problem one. It says a ball is thrown straight up into the air from a height of 1,280 feet with an initial velocity of 64 feet per second. Now notice they gave us a position, they gave us a velocity, and they start asking questions like, when does the ball reach its maximum height? What is the height at that time? Etc. Now this is an acceleration velocity position problem. And the problem is, once we read the problem, we have to stop, not even read the questions they want us to answer, but come up with the acceleration, velocity, and position equations by using antiderivatives. Once we have the equations, we can pretty easily answer their questions. So what I'm going to do, I'm going to go to the whiteboard, and we're just going to use some really easy antiderivatives and try to come up with your equation. Now the first thing they said was a ball is thrown straight up into the air from a height of 1,280 feet with an initial velocity of 64 feet per second. But I insist that this is an acceleration velocity position problem, which means we have to, in this problem, know the acceleration. Now there are two different accelerations of gravity that are used. There's minus 9.8 meters per second squared, and there's minus 32 feet per second squared. And the context is what's going to give us this. In this case, everything's measured in feet. I would tell you in Calc 1, over 3/4 of the time, they're going to give us feet and feet per second. So that we're stuck with that. So what I want to be able to do is just write down the acceleration. Well, the acceleration in this case is going to be minus 32. So I'm going to write it like that. Now, what did I say? I said we're going to use antiderivatives. How can I use antiderivatives here? We have to remember that the definition of acceleration is the derivative of the velocity. So from here to here, I'm just going to take the antiderivative of the left-hand side, antiderivative of the right-hand side, and I'm going to get something like minus 32t plus c equals v of t. Now, I'm calling it v of t because it clearly depends on time, whereas the acceleration did not. Now in practice, what we try to do is try to figure out what the constant is. Otherwise, I really don't have an equation. Now, how am I going to do that? I am going to go back to the question. And the question says a ball is thrown straight up into the air from a height of 1,280 feet that has nothing to do with the velocity, no help so far, with an initial velocity of 64 feet per second. Initial velocity. Initial, remember, initial, it means at the beginning. So they're telling us that the initial velocity was 64. Now, how does that help here? Well, this equation here for the velocity says if you tell me time t, I can plug it in and find the velocity at that time. So if I want the velocity at time 0, I put a 0 there and I just get c. Now we now know that c is 64, so we can actually get a much better equation for the velocity. I'm going to get minus 32t plus 64. So we're 2/3 of the way of finding the equations. We have the acceleration equation, we have the velocity equation. We now need the position equation. How am I going to find the position equation? I'm going to remember the definition of velocity. The definition of velocity is the derivative of position, like that. That's what I'm going to do with this piece right here. I'm going to take the antiderivative of the left-hand side, antiderivative of the right-hand side. Antiderivative of the left-hand side isn't so bad. It's actually probably easier than anything else we're going to do, right? Is minus 16t squared plus 64t plus a constant. I don't want to put plus c, and I don't want to start using subscripts. What I'm going to do, you can do what you want, is put down a letter that's close to c that still can stand for a constant. So I'm just going to put a big fat D right there. Now what is that? That is our formula for position. Now I have to figure out D. At least I can try to figure out D. Some of these questions I can't figure out D at this stage, but here we go. Did they give us any information about position? I think they did. Going back, a ball is thrown straight up into the air from a height of 1,280 feet. That is about position. Yes, in fact, what they're telling us, right, is that the position at the very beginning of the problem is 1,280. By the way, that's not quite as tall as the Empire State Building, but it's pretty close. Throwing balls up there, I'm thinking is illegal, but here we go. How does this equation work? It says you tell me t, and I'll tell you the position. So when I put a 0 there, we get d, like that. And so we actually get a better, or actually at least a complete formula for position. It's going to be minus 16t squared plus 64t plus 1,280. And that finishes the first part. We now have an acceleration equation, a velocity equation, and a position equation. In the second little video, we are going to use those three equations to start answering their questions.